Now, I've mentioned before that our computer systems use binary, and we know they use binary. And so every number is stored in the computer as binary numbers. That's all it does. So the memory in the computer only has binary numbers in it. And in the past, those numbers were 8 bits long. And when I say the past, I mean the old days when I was young. Then they doubled and they were up to 16 bits. And then they got even bigger, that they were 32 bits. And today, and of course I'm talking about computers, that the computers we have in front of us now, not the mainframes and big computers. Because again, in the 70s I was working on a computer that had 60 bits long. It was a supercomputer of its day. But the PCs that we're used to working on. So we have 8 bits, 16 bits, 32 bits, and 64 bits. Now the size of these are as they get bigger. One of the things we've talked about is binary, and we have bits, which are zeros or ones. You might see bytes. Now, bytes are, some people say a byte is 8 bits, but they're wrong. A byte is the size of the memory that you have in your computer. So your memory spot is 8 bits, it's an 8-bit byte. You have a 16-bit machine, it's a 16-bit byte. You have a 32-bit machine, you have a 32-bit byte. You have a 64-bit machine, you have a 64-bit byte. You might see people say bytes are only 8 bits. They're wrong, but you can humor them if you want to. Now, the reason they say that is because we use a system called ASCII to represent characters, A, B, C, all the way up, using 8 bits. So a byte is equivalent to a character, give or take some bits, and depending on how you're using it. And of course, that's not in all systems. I was talking about that 60-bit computer system I worked on before. It stored characters in 4 bits, which I'll maybe explain how they did that later someday. Now, we saw that 8 bits of binary doesn't hold a big number. It holds 255, which means if you had 8 bits, you could store a number from 0 to 255. Now clearly, computers were storing bigger numbers than 255 when we had 8-bit computers. Now we're going to look at different ways to store values in a memory location that doesn't just use the binary value. But the other thing is, these numbers are used to address the memory spaces. So if you had a 8-bit computer that only had 0 to 255, you could only have 255 storage spots in the computer, which isn't going to work. So you can put two of these together to get 16 bits to address a much larger memory space, which was very common. So the 8-bit computers that were used in the past often used 16-bit address buses to address a much bigger memory space. In fact, it was 64K, which is not 64,000, it's 65,000 something and something. It's 124 times 1,000, not 164. It's using a K as 124, not 1,000. Now in the 32 bits, they use the whole 32 bits for the address bus. In the 64 bits, they don't use all 64 because you could address a huge amount of memory that you're never going to need. And so they truncate it and only use so many bits on the 64-bit bus, on the address bus to do that, to address the memory. Now, with that in mind, if we had a 64-bit piece of memory in our computer, think about if you were storing a sentence and you had 8 bits per character. How many characters could you fit in here? You would do 8, 16, 24, 32, 1, 2, I'm going to run out of space. 1, 2, 3, 4, 5, 6, 7, 8. I did it. You could only fit 8 characters per memory spot. So if you had a whole novel stored in memory, you'd need a whole bunch of memory. But even if you had this, that's 8 bits per character. Let's say A, B, C, D, E, F, G, H. You still can't say that it's a character. It's just a string of bits. It's 64 bits. 64 numbers, are they letters? Are they numbers? Is it an integer? Is it a floating point? Is it a color on a JPEG? Is it an intensity? Is it a command in Python? Everything is stored in binary in the computer. It's all one big list of binary numbers. And you can assign those numbers to be whatever you want them to be. However you store them doesn't mean that's how you're going to look at them. If you've done programming before and you declare a variable, in some languages when you declare a variable you have to say what type it is. And the reason you do that is that way the computer knows I'm going to look at this as a character. So I'm going to be looking at this as ASCII characters. So that string of binary numbers is an ASCII value. Other computer systems, say Python, lets you store it however you want it. It's only when you read it out that you tell it, oh, I'm going to read that as a string, or I'm going to read that as an integer, or I'm going to read that as a floating point. But it's still just a string of binary numbers. The computer holds binary, that's all it holds, and it's not necessarily a binary equivalent of a number. So we have different ways of storing numbers in the computers. One of those is as a straight integer, which is, and of course, we haven't talked about negative values, but that even makes it harder to do. But it can be a straight integer value, it can be a real number. One of the other ways to encode it is called binary coded decimal. Binary coded decimal, or you might see it as binary encoded decimal, BED, but it's really binary coded decimal. And what we do with that is, instead of doing the values of the number of items we counted, so instead of saying 207 and then converting that to binary, all we do is convert the 2 to its binary equivalent, the 0 to its binary equivalent, and the 7 to its binary equivalent. So 2 becomes 0010, 0 becomes 0000, and 7 becomes 0111. And this is the value 207 stored in a computer, but it's stored as binary coded decimal. This value does not add up to 207 items. And so even when you store integers, you can store them different ways in the computer, and the values are not necessarily the same as how it's stored. So we're going to look at how to convert some of those in later weeks as well.